planet Earth is a tiny speck of dust in the universe. Its average diameter is 12,742 kilometers. For those of us who are used to measuring distances in meters and kilometers, it is difficult to understand the global scale of the entire universe. A unit of measurement used for convenience within the solar system, an astronomical unit. 150 million kilometers, or the distance from the Earth to the Sun. With the planet Pluto behind the solar system, our light is an average of 40 AU, or about 6 billion kilometers. But in outer space, the gaps are huge. Therefore, a unit of measurement such as the light year is used for convenience. Light travels in a vacuum for a year. For example, light from Pluto to Earth takes 5.5 hours, so the distance is 5.5 light hours. But Proxima Centauri is 4.2 light-years away from our nearest star. To the nearest large galaxy in our local group, the Andromeda Galaxy, 2.5 million light-years. But that's still not much. Today we're going to go even further by exploring the large-scale structure of the universe. Thus, the first indication of large concentrations of galaxies larger than individual clusters came from the work of William Herschel and his son John Herschel. They found a galaxy far away from the Milky Way, and we now know that most of them are galaxies, is very unevenly distributed. 1/3 of the region is in the 8th part of the sky, in the center of the Virgo cluster. In the 20th century, the dramatic increase in astronomical observational capabilities led to rapid progress in the study of the wide distribution of galaxies. Over time, it became clear that a single galaxy is very rare. Already at the beginning of the 20th century, stars have been known to break up into star clusters, which in turn form snowflake-like galaxies. Gravitationally bound galaxies form clusters and superclusters of galaxies. Superclusters are the largest type of association, containing thousands of galaxies. In addition to large interstellar islands, these large stellar structures also contain clusters of highly heated gas. A qualitatively new level in the study of large-scale structure was achieved by obtaining mass estimates of radial velocities and redshifts of galaxies. The value of the radial velocities, which characterize the distance to galaxies, has made it possible to construct three-dimensional maps of the wide distribution of galaxies for some selected regions of the sky, measuring more than 1 billion light-years. Large-scale structure has also been discovered from observations of gamma-ray bursts. Gamma-ray bursts are the most powerful bursts of energy in the observable universe and occur in massive and distant stars orbiting at high speeds. Such outbursts are rare. For example, in a galaxy the size of the Milky Way, they occur once every few million years. Thus, the lights are quantitative indicators of the intensity of the decomposition of matter, that is, the activity characteristic of galaxies, and the large number of lights imply a high concentration of matter and, consequently, a large number of galaxies. Analysis of the distribution of galaxies and their velocities has led to the conclusion that superclusters cannot be considered coherent systems like clusters. Superclusters, as it turns out, are not clusters or islands of individual galaxies, but denser regions and fibrous structures in space formed by galaxies and their systems. Some analogues of this structure can be the foam of soap bubbles. It is true that the distribution of galaxies along the cell walls is not very uniform, unlike that of a soap solution in bridges, and the shape of the cells is not regular. Large cells are a few tens of megaparsecs, or hundreds of millions of light-years in size, but there are many smaller ones. Clusters in outer space can vary in shape and size, from small chains, such as the Markarian chain, a few galaxies, and the Virgo cluster, to walls such as the Great Sloan Wall, on a scale of 300 megaparsecs. The universe is nearly uniform and a collection of filamentary clusters of galaxies separated by insignificant regions. These areas, voids or voids, are on the order of hundreds of megaparsecs in size. In such places, the density of galaxies is at least 10 times lower than average. Filaments and voids can form extended, relatively flat, localized structures called walls. The first observed superscale object is the CFA2 Great Wall. located 200 million light-years away and about 500 million light-years across and a staggering 15 million light-years across. The Great Cluster of Quasars is 4 billion light-years away, and the open wall of Hercules, the northern corona, is more than 10 billion light-years away, or 3 megaparsecs. This large flat structure of galaxies is about 10% of the diameter of the observable universe. To us, such a wall passes through the Hydra, Centaur, Telescope, Rooster, and the southern stars of India. The galaxies that form it have radial velocities of several thousand kilometers per second, and most of them are at least 25 million light-years away. This wall includes the Videvi cluster and the entire local group on the periphery, the local group of galaxies that includes our Milky Way. Because we are close to the edge of this wall, the galaxies that make up the wall form a relatively narrow band across the sky, stretching over 180 degrees. And the galaxy stars appear to us like a cluster of Milky Ways in the sky. The universe can be considered homogeneous over a scale of a few hundred million light-years. For example, a cube of this size or larger will contain roughly the same number of galaxies, galaxy clusters, or voids no matter where it is placed. And on smaller scales, the distribution of galaxies is not considered uniform, or even approximate. This important result should be taken into account in the development of the cosmological theory of the evolution of the universe. Analysis of a three-dimensional model of the distribution of galaxies shows that pure structure can be observed in any direction for more than 1 billion light-years. This data shows that on a scale of several hundred million light-years, any fragment of the universe will contain the same amount of matter. This proves that the observable universe is uniform on these scales. Despite the presence of large-scale structures such as galactic walls and filaments, the largest stable structures are still thought to be clusters of galaxies. The fact is that the known expansion of the universe gradually expands the structure of any object, and only gravity can fight this force. Observations of clusters and superclusters have revealed a gravitational lensing effect, in which light rays traveling through interstellar space are bent, suggesting a large invisible hidden mass. It can enter various unobserved space bodies. However, on these scales it is likely that dark matter is responsible for the attraction and retention of galaxies and the formation of their clusters. The nature of the mysterious black mass is still being explained. Several possible variants of the initial particles are considered. But it is already understood that this invisible medium plays a major role in shaping the large-scale structures of the universe. Without the involvement of dark matter, it would be difficult to explain how the 13-14 billion-year expansion process could have produced the fine density inhomogeneities seen in the light distribution of the background radiation is observed. Complex structure formed from galaxies. The world of stars and galaxies would apparently not have formed at all, and the universe would have remained structureless, unless the gravitational field of ordinary matter is enhanced by the presence of non-luminous mass. But based on the uniform relic radiation, researchers believe that matter in the universe is distributed uniformly. But the peculiarity of gravity is that it pulls any physical particles into dense structures, thereby disrupting the equilibrium. Thus, sometime after the Big Bang, small imbalances in the distribution of matter in space began to grow into certain structures. As the mass increases, it gradually slows down until it stops completely. Moreover, in some parts, the expansion turned into contraction, which gave rise to galaxies, galaxy clusters, and the large-scale structure of the universe in the form of a three-dimensional cosmic web and the gaps between the threads. This is the web. Research in recent years has concluded that a rich picture of the present cosmic structure was created in the first moments after the Big Bang, when a homogeneous and rapidly expanding primordial cloud fell on top of it. Over 14 billion years of evolution, this ripple has been magnified to enormous proportions by gravity, creating ever higher concentrations of simple matter where simple gases cool, condense, and form galaxies. This process can be accurately reproduced in large computer simulations. The current theory of the formation of large-scale structures, such as individual galaxies, is called the hierarchical theory. Its essence boils down to the following. Yes, on very large observational scales, the universe must be uniform and isotropic. Random variations in the mass and structure of matter between different regions of the universe must be very small. According to modern concepts, the scale at which the equinox must have formed is about 300 million light-years. This is called the apogee of greatness. There should be no uneven structures of large size. But the giant walls that have been discovered are billions of light-years larger than the predicted scale. The irregular structure of the Hercules northern corona is more than 30 times larger than predicted. Of course, this calls the cosmological principle into question. Furthermore, the 10 billion-year interval is the same as when we observed this structure 10 billion years ago, or 3.7 billion years after the Big Bang. Existing standard models of the evolution of the universe do not allow for the formation of such complex and massive structures at such a stage. There is still no hypothesis as to how such a large structure was formed in such a relatively short period of time. Thus, radiation is a necessary component of the large-scale structure of the universe, without which it is difficult to understand how the world around you and me came into being. If we look at the night sky, we may think that the stars are spread out infinitely evenly in space. But this is clearly not the case. Stars gather into galaxies, and clusters of galaxies form clusters that are bound together by gravity. In general, the situation is such that the neighboring galaxies are located relatively close to each other, and the gap does not spread over large areas. But there are special cases like Valapasa Gap. This is an incredibly large area of empty space. It's 7 million light-years away, but its diameter is even more staggering, estimated at 330 million light-years. For 40 years, the Great Void has been surprising in its size and properties, forcing the most unusual hypotheses about its nature. But before we dive into the void in the sense of not getting discouraged, we look at the constellation where it is located. The Boötes constellation was recorded by Ptolemy in the 2nd century. The name comes from the Greek word meaning plowman or shepherd. It is located in the northern hemisphere and is one of the largest stars in the sky. If we travel to the Great Void, we'll encounter several prominent stars along the way. Consider them from a distance. Closest and most prominent is, of course, Arthur's star, an orange giant, the third brightest in the sky and the brightest in the northern hemisphere. It is 37 light-years away, 110 times the distance from the Sun. It moves at a speed of 122 kilometers per second faster than the solar system. One will make its closest approach to the Sun in about 4,000 years. Mufrid is a spectroscopic binary star, 494 days. Both stars are about the same distance from the Sun, about 37 light-years. One of the stars, Mufrid, is a G0 star with a surface temperature and color similar to the Sun. Mufrid is a subgiant. The star is on its way to becoming a red giant. Farther away, 51 light-years away, we see Tahualapasa, a double star represented by a yellow-white halo and a purple halo. Then the star Sejanus is located 85 light-years away. A variable delta shield-type star exhibits changes in brightness due to radial and non-radial pulsations. Star Alcalirops, it's not a drug at all. 3 stars, 121 light-years. Then we pass the constellation Merga. It is in spectral class F7. Star Necker, a G-type yellow giant. It is now 219 light-years away. It is a flaming variable star that increases in brightness for several minutes. The star Nadlad is a K-type orange giant, 250 light-years away. The star Isar is a binary star about 300 light-years away, represented by a bright orange giant and a smaller main sequence star, and many other stars. As we quickly approach the Great Void of Valapasa, we see that there are other voids. Although modest in size, we know today that these are the largest formations in the structure of the universe, and that they occupy its vastness. According to some estimates, this percentage is up to 50%, and due to gravity this percentage will increase due to the attraction of surrounding matter. We can determine the existence of a vacuum by the low density of ordinary substances. These smaller masses often contain neither galaxies nor stars. However, the internal space is filled with some content. What does it consist of? Voids consist of protogalactic clouds of dust and gas that later form galaxies. There is only speculation about the second compound, based on the reactive nature of the light passing through the warts. The reason for this may be that dark matter does not have its own electromagnetic field, so it is impossible to conduct research using known scientific methods. We have evidence that this is the case. The study of space is currently of great interest to you and me, physicists and professors, but a special case called Boötes void now attracts our attention. If we wanted to see what was inside, we would have to think about the deep black. This is dangerous. They discovered this loophole long ago, 40 years ago, in 1981. Robert Kirchner did it. During this time, many theories were popularized that the site was a result of the Big Bang, a super black hole exploding everything around it, a sickle surface, or that the textures were not loaded. But we know that this region exists in the shape of a sphere. More importantly, there are still galaxies in this region, just a few of them. First, the researchers wondered how many galaxies there are in this void. At first there were only 8, but after a long study, 60 were found. But it's incredibly small. If our galaxy was at the center of this void, we would have known about the existence of other galaxies 60 years ago. If we compare it to the Milky Way, it has more than 20 neighbors in 3 million light-years. If we compare the average density of galaxies in the universe, there should be 10,000 galaxies in the void, and there are only 60. Of course, visitors to this region would be surprised by such isolation, seeing the vast distances between galaxies and the blackness of deep space. In addition, the Boötes vacuum is probably the most perfect vacuum in space, and its effects are also worth considering. Not only rocks and dust, but also particles of all kinds would be rare. If it is possible, it would take periods for the particles to interact in this vast vacuum. This region of space has a very low density of matter, some structure, when a neutrino hits it. For example, on the one hand, it would be the same on the way out after hundreds of millions of years. The same is true for photons. Particles of matter have much more mass than neutrinos, and photons would naturally be attracted to the edge of the void. Due to this storage property of the empty state of Boötes, one day can be thought of as a perfect time capsule. As possible, the discovery of the supervoid had a major impact on traditional cosmological thinking. Since then, the scientific community has repeatedly reconsidered the formation of galaxies, taking into account what is known about the highly uneven distribution of matter in the universe. But how can this be? How could such a large gap exist? Smaller regions appeared, probably because gravity brought galaxies closer together, but no one knows how to explain the appearance of larger regions. However, attempts to find an explanation have led to the development of a new theory that supervowels are formed by the addition of smaller vowels, such as B's. Interestingly, galaxies in space take interesting shapes. Tube structure. It doesn't sound like an accident, but it's an important detail. Furthermore, the Boötes void was probably formed after small particles coalesced, similar to the way soap bubbles coalesce into one large bubble. As for the bridge galaxies, they are probably the remnants of the boundary between small particles. But only time will tell if this prediction is correct. There are many interesting places in our universe. Much has yet to be discovered, but what is known is mind-boggling. As technique and technology improve, we can look further. Then it will take time to figure out what any discovery means. How old are you on other planets? It makes sense to say that there is one. The answer is yes and no. The fact is that different planets rotate at different speeds. Also, each planet has its own orbit. You have to take into account the mass of the planet and its gravitational pull relative to the Sun. As a result, days, years, and other timescales can vary widely across the planet. Figuratively speaking, on some planets you can still be a baby in a star diaper. When you were on other planets, you were already old and slowly sunsetting. Here on Earth, we take time for granted, never realizing it. For example, the way we measure our days and years is the distance our planet is from the Sun. It is time to revolutionize it and orbit it on its own axis. The same is true for other planets in the solar system. While we Earthlings count a day as 24 hours from dawn to dusk, the length of a day on another planet varies considerably. In some cases it is very short, in others it can last more than a year. Time to go to other worlds. For convenience, we have cloned you and distributed you to various planets in the solar system. Your copy is even on Neptune. Ethan did this on January 1st, 2000. It has been a long time since then, about 6,827 days. You are now on Earth 18. Congratulations, you've been approved for your first loan, but we will politely decline. Let's go on a space trip. We need to check your doppelgangers. Who knows what time he worked for them? Now your first clone is on Mercury. It also appeared on January 1st, 2000. Other things didn't work that way for him. Mercury is the closest planet to the Sun. The distance can be 70 million kilometers. Considering that it takes about 58 Earth days for Mercury to rotate 360 degrees, you should understand that you only get to see dawn on this planet once every 58 days. But it only takes Mercury 88 Earth days to rotate the main luminary of the system, so a year and a half is a day on this planet. Today you would be 77 years old. This is in 116 days. Yes, time is kind to no one. By the way, your next Mercury birthday will be on October 14th. Then, the planet Venus. This may seem strange until you know that one Venusian year lasts 224 days. Yes, Venus takes 224 days to complete an orbital period, but more than 243 days from dawn to dusk. Thus, one Venusian day is slightly longer than a Venusian year. Yes, you are old, but only modestly. You are 30 years old. This happened in just 28 days. Your next birthday is January 26, 2019. Mars is the fourth planet from the Sun and the seventh largest planet in the solar system. The mass of the planet is 10.7% of the mass of the Earth. Mars makes one revolution on its axis in 24 hours and 37 minutes. Therefore, one day on Mars is equal to one day on Earth. You will be 10 years old in 6,628 days. You will celebrate your 11th birthday without alcohol on October 22nd this year. In ancient times, people were believed to have lived on a great plain, although it was covered by mountains and depressions. B.E. This belief lasted for thousands of years until Aristotle in the 4th century saw a ship out to sea disappear from sight, not because it was compressed to an unacceptable size as it moved away, but on the contrary, first the ship's hull disappeared, then the sails, and finally the masts. This led him to conclude that the Earth must be round. What can we say about the universe? Do you have to wonder what form it will take? Is it possible to determine the shape of the universe as we did with the planet Earth? So what would you like to see? Infinite darkness? How much? A snow globe or maybe a maze? DS Logos? Determining the shape of our universe has proven much more difficult than thought. On the one hand, it can have a half-life and an infinite distance like the number 3, or it can have a complex shape and even be finite. Of course, any discussion of the possible shape of our universe must be based on real facts from astronomical observations. Without it, even the most beautiful and plausible hypotheses are doomed to failure. So let's take a look at what the observations say about the universe. First, remember that wherever we are in the universe, at any point in the universe, we can represent a region of magnitude that encompasses the space of the universe. This artificial construction tells us that the universe is a three-dimensional manifold. The immediate question is, what is the diversity that characterizes our universe? According to reports, there are many. The complete list is not yet available. However, science does not stop, and many years of observation have shown interesting results. There are several physical properties that drastically reduce the number of possible candidates for the shape of the universe. And one of such fundamental properties is the topology of the universe and its curvature. Of course, subtlety doesn't mean the edge of space is falling off like a crowded star. For example, the surface of our planet is limited, but going beyond this area will not work. With a positive curve, we get a four-dimensional area. This variety has an end, but no clear border. More precisely, the two particles would pass through it before returning to the starting point. You can also try this at home. Take a ball and draw a straight line until you return to the starting point. This type corresponds to 3 dimensions and occurs when there is a lot of energy in space. To completely curve or close, the width must stop expanding. If there is a large reserve of energy capable of creating an alien, this will happen. There is also a suggestion that the universe is called a 4-dimensional saddle. This form has no boundaries of space and time. There is very little energy, so the universe would not stop expanding. If you were to send 2 particles in a straight line, they would never meet. They would diverge infinitely from this realization until they diverged like the hemispheres of the brain. There is a concept that the universe is, yes, flat. If this is true, the critical energy will grow between the extremes, and after some time the expansion will stop. In such a universe, 2 particles would travel parallel but never separate. These 3 forms are easy to visualize, but there are many variations. A soccer ball brings to mind the idea of a spherical universe. And then, of course, there's the donut shape, technically flat, but connected at some points. Some believe that the large hot and cold spots found in the universe support this option. But let's go back first. Head. If we consider the Big Bang theory, there is no concept of here and there before and after. All the matter of the universe is concentrated in a single point of 0 magnitude, thus almost infinite density. There was no time, because nothing was at the point and nothing was beyond, so it couldn't happen. Then, for some reason, the dot exploded and began to expand. The newly born matter did not rush to anything in its surroundings at the speed of light. Energy and forces were created, atoms, electromagnetics, and gravity. And so time came into existence and began to flow. With this, we can even determine the age of the universe, which is about 15 billion years. If this is true, the answer to the question of the size of the universe becomes clear. If true, even a cardboard toy consultant can easily estimate the size of the universe. You need to multiply the time difference by the speed of matter, which is the speed of light, which is 300,000 miles per second. It is possible that this speed decreases slightly over the years, but for simplicity of calculation we consider it to be constant. Yes, that's a lot of numbers, lots of zeros, but still not infinite. Conclusion? The universe is big, but it is finite, so it should have not only the size but also the shape. This is where the fun begins. It is logical and easy to assume that the universe has a spherical shape. What would happen if matter were to fly away from a center at a constant speed? Whatever the shape of the sphere, the classical explosion refers to that shape. But what if the velocity is not constant and the universe is not closed or homogeneous? Then the shape changes a lot. For example, a straight or curved 4-dimensional plane. In this case, the universe does not close, eternal and infinite. But there is another interesting point. In the middle of the last century, the Soviet scientist Dmitry Ivanenko made a hypothesis that the universe, firstly, is closed, and secondly, the laws of Euclidean geometry are not everywhere obeyed. Hence, there are places where parallel lines cross and even flow into each other. For example, if we start from a certain point in the journey, say the planet Earth, and move in what appears to be a straight line, we will eventually find ourselves there, on Earth, and for many years. If this is true, then the universe is like a bottle, a pumpkin, or a trifle. Generally, in something like this, yes, we have looked at many shapes, but we have never been able to pinpoint them. That's good to know. To this day, the shape of the universe, the scientific community is trying to study relict radiation, because the big explosion released not only matter but also radiation.